So 11:05, we are continuing.
All right, thanks. So I want to show you some more examples and go a little bit more deeply into this. Before I show you this next example, I want to introduce you to a very important concept in machine learning called one-hot encoding. Here's the skinny on one-hot encoding. Machine learning models can only deal with numbers. At the end of the day, they're just looking at ones and zeros. They are not capable of handling text, which is a problem in a way, because what if we want to use machine learning to build a spam filter? Or we want to use machine learning to do sentiment analysis, to look at a review on Yelp or somewhere else and score it for positivity or negativity. That all involves text. The primary technique that machine learning models use to handle text in the models is something called one-hot encoding. It is a mechanism for turning a bunch of text strings into ones and zeros. Here's how it works. Let's say that you have a data set that has a column named company, and in that column you have company names like Microsoft and Facebook and King ICT. You want to use those company names in a model, but a machine learning model cannot use those company names in text form. So what you do instead is you one-hot encode the values in that column. One-hot encoding adds additional columns to the data set, one per unique value found in this company column, and sets the corresponding number there to a 1 or 0. That's a very simple way of turning, we call it vectorizing text, of turning text into numbers that a model can understand. And there's a method in ML.NET that lets me do one-hot encoding with one method call. The method name is one-hot encoding. Now, let me show you an example, a somewhat more complicated regression model. Then we'll move on to classification. So let's go back over to GitHub here. Let's end the slideshow first so you can see what I'm seeing. And let's see if I go here. Well, let's do this. We'll close PowerPoint. That will get it out of presentation mode. Okay, now let's go back over to GitHub. And let's look at a different project here. This one is called MLN Multiple Regression. And what we're doing here is very simple. This too is a command line app, so we can get most of what we need out of this file named program.cs. What we do here is I take a bunch of data from Zillow.com. It's a popular site in the US that's used to sell real estate. It's actual data regarding the sales of homes in a very expensive section of San Francisco called Pacific Heights. I have that data in a CSV file, and if you look inside the CSV file, you'll see that each property is characterized by things like the number of rooms, the number of bathrooms, the price that it last sold for, and other things. What we want to do is to be able to predict the price of a property that we sell there based on characteristics such as those. So in ML.NET, I create a new ML context object. I call load from text file to load the data from the CSV file. And then I use train test split to do an 80-20 split of the data, 80% for training, 20% for testing. Now, one of the columns in the data set is named use code. And in that column are textual values like single family dwelling, condominium, things like that. You can imagine that that characteristic might have a pretty substantial effect on the price that that property will sell for. So we need to incorporate it into the model. But again, an ML model can only deal with numbers, not text. So what do? I do exactly what I showed you in the slide. I one-hot encode the values in that use code column. Now, there are about 6 or 7 or 8 different strings in that column. That's going to add additional columns to the data set. I give those columns the logical name use code encoded. That's the way now in ML.NET I will refer to the group of columns that were added. Then I tell ML.NET that I want all of those columns that were added from the one-hot encoding, as well as some of the other columns in the data set, like the number of bathrooms, number of bedrooms, finished square footage, in that magical features column. Then I tell it that I want it to use a fast forest learning algorithm, and here I fit it to the training data. In other words, I train the model. Now, if I could actually run this, you could see this probably takes 30 seconds to train. There are only a few hundred rows in the data set. After I train it, I want to find out how well is this model going to be able to do predictions. So I call evaluate, and I output the R2 score. And if I recall right, this falls around 75 or 76%. Not bad, but I could do better by tuning this, by adjusting some of the parameter values passed into the fast forest algorithm right here. But as usual, I'm defining classes named input and output. Again, the names are not important. You can name them anything you want. But this gives me strong typing of the data that I put into the model and the data that I get out, and maps these property values back to the corresponding columns in the data set. That's something you'll see time and time again in ML.NET, where we create strong types around the data that we're loading from the data set. Okay, let's go back to PowerPoint for just a moment here. And actually, no, I want it right here. Here we are. And let's get down to the next slide I wanted to show right here and start the slideshow. So those are the basics of regression models. And again, I'll give you the URL for this GitHub repo so you can download all this and run it on your own machine and see for yourself. Let's talk about classification models, though. Models whose purpose is not to output a numeric value like the sale price of a home, but to classify the input into categories or classes that we specify. There are two types of classification in machine learning. There's binary classification, where we try to classify something into one of two classes, spam or not spam, for example, if you're building a spam filter. There's also multi-class classification, where we specify more than two possible classes. We train the model and then allow it to predict from future inputs which class that data most likely belongs to. That's commonly used in applications such as optical character recognition. ML.NET contains about a dozen different binary classification trainers. I've listed them right here. Remember, these algorithms, this code has been in Microsoft for almost a decade. It's been used by a lot of the product teams there. So it's been tested, it's been tuned, it's been tweaked. And it's not always obvious, by the way, even if you do a lot of machine learning, what algorithms these implement, because sometimes they're sort of hybrid algorithms. The good thing is, this library is open source. So at the end of the day, if you need to know exactly what one of these learning algorithms is doing, you can go to GitHub, you can look at the source code there. But let's look at an example here. Before the example, let me tell you about one of these classification trainers. It's a learning algorithm that's incredibly important in the world of machine learning. It's called SVM for Support Vector Machine. And it's one of these algorithms where if you go do a search, you'll find all kinds of scholarly articles on it. None of them will actually tell you how this works. What they will do is kill you with big, long equations. But SVM is actually very, very interesting, very useful for the simple reason that when you have data that cannot be fit by any other learning algorithm, there's a good chance SVM can do it. What SVM does in essence is it synthesizes dimensions. It adds new dimensions to the data so that the data becomes linearly separable. As an example, look at those data points in the upper right-hand corner. I have those blue squares and I have those black dots. That is not a linearly separable data set. There's no line that you can draw through there that would have all of the black dots below the line and all of the blue squares above the line. But with SVM, we can play a little trick. Notice that the black dots are much closer to the origin than the blue squares are. These are two-dimensional points. They have x's and y's. We're going to synthesize a z, a third dimension, from each point's distance from the center. That means if you could take that two-dimensional chart and imagine it in 3 dimensions, then the blue rectangles are closer to your eye than the black dots. In fact, in that second chart there, I've rotated the thing 90 degrees around the x-axis. And now, lo and behold, there is a line or a plane that we can draw that provides a nice clean separation of those points. That is the crux of support vector machine. Coding it by hand is incredibly complicated, but guess what? There are classes in ML.NET that simply do it for you. Let's go take a look at an example. There's one more thing I want to show you first, because this next example will be meaningless without it. We've already talked about the fact that machine learning models cannot deal with text. We have to vectorize the text somehow. We by turning it into ones and zeros. One-hot encoding is one technique used for doing that. One-hot encoding is specifically used to encode what we refer to as categorical variables. If a column in a data set has the make of a car, for example, like Ford or Volkswagen or Skoda or something else, those are categorical values that we transform into vectors or ones and zeros using one-hot encoding. But what about the more general case? What if you're trying to build a spam filter, which is one of the classic uses for AI today, where you have maybe tens of thousands, even millions of words, and somehow you need to vectorize those. The way we vectorize arbitrary text for use in machine learning is by doing something called text featurization, also called text vectorization sometimes. What we do is we take all the text. Imagine these are content from emails that we're using to train a spam filter. We go through all of the text. We build a big dictionary that containing each word that we encountered in the text. Then, to represent each of the individual emails or the text in them, we create rows of ones and zeros, where the columns in the text correspond to the words found in the text that are present in the dictionary, and the cells have ones or zeros indicating whether that word is there or not. This is how we build spam filters. It's how we do sentiment analysis. We take these big corpuses of text and we turn them into big tables, sometimes tens of thousands, hundreds of thousands of columns wide, filled with ones and zeros, indicating which words from the dictionary were found in the data that we're training with. Now with that, we can see how we might use ML.NET to build models that deal with text. So let's pop back over to GitHub real quick. Now let me show you how you would use ML.NET to build a spam filter. A very good one, as a matter of fact. This project is called MLN Spam Detection. Let's go into it, and once more we'll look at the program.cs file. This too is just a simple command line program. So we start with the data, which comes from a file named hamspam.csv. Let me tell you where this came from. In order to build a spam filter, you need emails, lots of emails, preferably millions of them. And someone has to meticulously go through each email and mark it with a 1 or a 0, indicating whether it's spam or not. Fortunately, those data sets already exist in the public domain. The one I'm using, 20 years or so ago in the United States, we had a huge scandal around a company called Enron. They were an energy company in Texas. They ended up going under, the leaders of the company went to jail, stuff like that. After all of that was said and done, the millions and millions of emails that Enron had aggregated over the years became the property of the United States government. They're now part of a public data set. You can go download those emails. And at, I think, University of California, some data scientists meticulously and laboriously went through all those emails, marking each of them with a 0 or 1 for spam or not spam. This is another reason that machine learning is advancing so quickly today. Used to be, to get that kind of data, you had to build it yourself. Now there are lots and lots of public data sets like that, specifically for building spam filters and other types of machine learning models. So I've taken a small subset. I think I pulled out 1,000 emails, 500 that are spam and 500 that are not, put them in this CSV file right here. Then I load the contents of the CSV file into a data view. I do an 80-20 train test split, so I can train the model with 80% and test it with 20. And then I use ML.NET's handy featurized text method. This is where the magic happens. I feed it all the data in the column that contains the text of the emails itself. And inside that call to featurize text, a lot of things happen. All the text is converted to lowercase. Stop words, that is meaningless words like the and are removed. You can customize that if you want to. And ML.NET builds that big dictionary containing a list of every word that it finds in the training data and produces those rows of ones and zeros to vectorize text that I can use to train a machine learning model. All of that happens inside that featurized text method. That featurizes it. Now I can use it to train a model. I do the training right here by calling fit. It's a binary classification model. Every email in this data set is marked with a 1 or a 0 for spam or not spam. I evaluate here, and if I could actually run this, it would tell you that it is about, I think it's around 95% accurate, and that's with just 1,000 emails. If I trained it with 100,000 emails, which are available, I would expect to get up well above 99%. And as usual, I define my data schema down here in my input and output classes. You can see that I have a column of ones and zeros, which I call is spam, that indicates whether that email is spam or not, and a column that contains the text from the body of the email, which I simply call text. Now, for the output class, there's a little bit of magic that happens here. Your output class for a binary classification model in ML.NET needs to have two properties, one named prediction, one named probability, and that prediction property needs to be attributed predicted label. When you do that, when you run the model and you get an output object back, prediction will be a 1 or 0. It'll be a true or a false, telling you whether the model thinks that the email that you just fed into it is spam or not. Probability is a value from 0 to 1, indicating how certain it is of its prediction of the true or false. And if you actually run this, I've got some sample text up here, some sample emails. You can run them through. You can even create ones of your own. You'll see that it's actually astonishingly good at detecting whether an email is spam or not. One other example really quickly, I won't go through all the code, but I'll make you aware that it's there. This one also does binary classification, and that is sentiment analysis. Very common problem in machine learning is to want to take text strings, reviews from Yelp or a movie review site or something like that, and score each of those for sentiment, where generally 0 indicates very negative sentiment, 1 indicates very positive sentiment. My son finished grad school back in December. He's now a degree data scientist. And last summer he interned at a company in the United States that sells pet products. And his very first assignment when he went into his internship came from the marketing department, where they wanted him to build a dashboard that would monitor tweets that target that company, evaluate them for sentiment, and alerts the marketing department if it falls below some threshold. The idea being that if people are tweeting negative things about the company, they want to know about it so they can get out and respond. Sentiment analysis is a problem that was figured out a long time ago in machine learning, and it's very easy to do. Once more, I took a pre-existing and very public data set to train the model. A lot of the code looks very much like what you saw in the previous example. Notice the call to featurize text to featurize all of that text. And then at the end, when I feed a text string into it, it gives me a score between 0 and 1, indicating how negative or how positive this is. And if I could run this, when it says I wouldn't let my dog eat here, it scores at about 0.0003, as I recall, whereas it scores this up in the high 90s, like 0.98 or 0.99. So it's pretty good at doing it. And I'm training it with, I think, less than 10,000 reviews. But there are many more available, so if you wanted to make it even more accurate, you could expand the data set that you're training with ML.NET. It may take longer to train, but you should not have to worry about running out of memory. By the way, when you do apples to apples perf comparisons on training with ML.NET and scikit, ML.NET's typically 5 to 10 times faster. And unlike scikit, which cannot innately use multiple cores or multiple CPUs, ML.NET does. So, the more cores you have to throw at it, the greater the perf difference will be between ML.NET and other libraries like scikit. Okay, let's go back over to PowerPoint for just a moment. We have about 10 minutes left, and we have some cool stuff to show. Let's get back to where we were. Now, I won't look at this example here, so I can use the remaining 10 minutes for something else, but there are also a number of classes in ML.NET for doing multi-class classification. One of the examples in this GitHub repo that I'm using does OCR. It takes a public data set of scanned handwritten digits that came out of the University of California, Irvine, and it trains a model to recognize when you draw a digit like a 0, 1, or 2. It trains the model to look at that pattern of dots and tell you with more than 99% accuracy what digit you just drew. That's a multi-class classification problem because for each row of numbers you feed in representing that bit pattern, there are 10 possible classes that it can belong to, the digits 0 through 9. So that's sitting in the GitHub repo. You can look at it. It's a great example of multi-class classification. But one thing I want to make sure you're aware of before we end is something that is super, super cool. Some of the more magical things that are accomplished with AI today involve image classification. Looking at an image and deciding whether it shows a well-formed part or a defective part coming off an assembly line. Looking at an image, deciding whether that image contains a hot dog or a slice of pizza or whatever. 10 years ago, these kinds of problems were almost impossible. Today, it's a well-understood science thanks to a special type of neural network called a convolutional neural network, or CNN. Let me show you just a little bit about how these CNNs work, and then describe to you how you use ML.NET to do them. A convolutional neural network excels at doing things like facial recognition, object identification, things like that. And the way they work is kind of interesting. They actually borrow a trick from Photoshop. If you've ever used Photoshop to blur or sharpen or emboss or do edge detection in an image, the algorithm that Photoshop uses to do that is something called a convolution kernel. It literally takes typically a 3x3 or 5x5 matrix of values, passes them over the image, transforms every pixel using some matrix math with the values in that convolution kernel. One thing that allows us to do is things like this. If I take that image of a hot dog and I take the convolution kernel underneath it and I pass it over every pixel in that hot dog image to transform the pixel values, the result is what you see at the bottom. That is an edge detection convolution kernel. What's important about that is this is how convolutional neural networks learn to recognize features in images, like the shape of a cat's ear, or the shape of a dog's tail, or something like that. Convolutional neural networks run multiple convolution kernels over the images that you train it with to learn the shape of the things that you're asking it to detect. Then they will subsample the image down to half its size, do the whole thing over again. Then they'll subsample it down again. What is it doing? It's making sure that it can recognize features in those images, not only at a micro level, but at a macro level as well. Once the images that you train with have gone through all of the convolutional stages of the neural network, they go through a pair of what we call fully connected layers, layers of neurons that typify a neural network. That's where the classification is done. That's where we tell the model that we train, yeah, those images I just trained you with, there's a cat in each of those images. This batch of images I trained you with, there are dogs in those images. Once I do that, a convolutional neural network can typically, with a very high degree of accuracy, do image and object detection in new images that I feed in. Now here's the problem. The state-of-the-art convolutional neural networks that are used to do image detection today are not something you and I can build. They are super complex, super sophisticated. They're primarily built by data scientists in Microsoft Research, at Facebook, at Google, and a few other tech giants who are paying high salaries to hardcore data scientists to build new neural networks. Even if we knew how to build one, we would have no hope of training it. Because for these convolutional neural networks to actually do image classification and object detection, they typically need to be trained with at least tens of thousands of images, preferably hundreds of thousands or millions. You're talking trillions of pixels that you're training with. The data scientists at Microsoft and Google, the way they train these networks, they spin up huge HPC, high-performance computing clusters in the cloud in Azure or AWS. And these clusters are equipped with GPUs, graphical processing units for parallel processing. The cost is probably hundreds of thousands of dollars per run because these virtual machines are very expensive. That's why it's pretty much only something that the tech giants can do. But guess what? There's a technique called transfer learning that lets you take the networks they've already built and trained. By the way, they put these things out on GitHub so any of us can use them. And repurpose it so that with a minimal of training, and typically with as few as 50 to 100 images, we can take one of their already trained CNNs and we can repurpose it to say, okay, I know you were originally trained to recognize whether an image contains a cat or a dog. I want you to instead recognize whether it contains a hot dog or a hamburger. It's not easy to do this with most libraries. ML.NET, in my opinion, makes it easier than any library in existence to do it. I won't go through the code. It's a lot more meaningful if I can run it to show you that it works. But let me show you where it is on GitHub so you can look at it yourself. Let's go back to GitHub here. And the project you want to look at is, there are two of them. There is MLN image classification and MLN not hot dog. If you look at the MLN image classification project, I take a 50 megabyte TensorFlow model built and trained by Google. It's not the most sophisticated in the world, but it's in the top 10. There's literally a 50 megabyte zip file containing that TensorFlow model in the project. I write about 20 lines of code in ML.NET to subsume that model and to retrain it to recognize whether an image contains a hot dog or not. The other project is named MLN Not Hot Dog, and it's inspired by the Not Hot Dog app on the HBO show Silicon Valley. It's a WPF app that uses the trained model. It lets you upload an image to it, and it tells you whether that image contains a hot dog or not. In total, there's about 20 lines of code in it. Transfer learning is something that every software developer should know about because it allows us to do things like build apps that determine whether a part coming off an assembly line is defective or not. But rather than try to build those neural networks from scratch, which is not practical, we use transfer learning to repurpose existing networks to do our bidding, to solve our domain-specific problems. There are other libraries that help you do this. You can do it in TensorFlow, although it's horrific. No library makes it easier than ML.NET, and if this is something that's interesting to you, you should check out those examples right there. Final thing I'll mention about ML.NET, actually two things. First, let me give you the URL of my GitHub repo so that if you want to download these samples, you may do that. Oh, there it is. And it should be the last slide here. Here's the end key. There we are. All the samples I showed you and some I didn't are in that repo right there. The last thing I'll mention with ML.NET is a feature called AutoML. It was funny. A couple of years ago, my son and I were sitting around the dinner table. We talk data science at dinner, and which doesn't make my wife super happy, but she understands, you know, it is what it is. And we said, you know, rather than know, you've got to figure out which algorithm to use. And then you have to play with different settings for each algorithm to find the optimal combination. There's just so much manual effort involved in doing that. Why doesn't someone build a tool that will do that for us? ML.NET has done that. It's called AutoML. There's a sample in my slide. There's also a sample in the GitHub repo. You simply give it a data set, and you tell it to go to town. It uses AI to discern the contents of the data set. It does any hot encoding that's needed automatically. It does any text featurization or vectorization that's done automatically. And it tries out all the algorithms that it thinks might produce the best results, and even experiments to find the proper parameters to that algorithm to give you the best results. Now, it can take a while to do. It can take hours on a dual-core machine like my laptop. But if you're willing to do that, it will sit down and crunch the numbers and find the best model for you. There's also a plugin for Visual Studio called the ML.NET Model Builder that uses that AutoML capability. You can use it through Visual Studio, or you can just write the code. 10 lines of code will create any model you want. Sit back, let it run overnight, and you're going to look really smart because you'll probably come up with a really good model, and you did basically nothing to make it happen. That's my idea of a great library. Thank you so much. Hey, listen, we don't have time for Q&A, but I'm going to be floating around out here for a little while. If you have questions, you want to talk ML.NET or machine learning or something, find me. I'll answer all the questions you have. We'll chat. Thank you so much.
Thank you, Jeff. This was amazing. Please rate the session on Eventify.